what about this? R minus Q and R in bijection with each other. Are these two in bijection with each other? Does anybody know how to do this? Okay, I'm going to write down. Yeah. So let us start with this. All of you understand disjoint union? Okay, so R disjoint union Q is equal to, yeah, R minus Q disjoint union Q I simply partitioned reals into irrationals and rationals, and then there is one more copy of rationals. Now using associativity of disjoint unions, well, I can simply write it down as R minus Q disjoint union Q disjoint union Q. Any problem with this? Yeah, I simply shifted the parenthesis from here to there. It's disjoint union ultimately, doesn't matter. Now look at the parenthesis on the right hand side. Q disjoint union Q. Q is a countable set, so finite union of countable sets is, and these are both countably infinite, so therefore their finite union is countably infinite again. So therefore this is in bijection with R minus Q disjoint union, just one copy of Q. Why should I write two? It is again countable, so therefore I can write 1, and which is in bijection with real numbers, because I simply put those rational numbers back in. Yeah, magic. Similarly, yeah, I can start with R minus Q and take out one more copy from, I can start with real numbers. I could have started with real numbers and taken out two copies of rationals, like two countable subsets, and done the same thing. Yeah, so similarly prove, yeah. Prove R minus Q and R have the same cardinality. Basically, if your set happens to be uncountable, then it doesn't matter if you take out a countable subset of it. Your cardinality is not going to change, your size is not going to change. You will still remain in bijection with that set. Yeah, this is the argument. Yeah, this is simple argument. As long as you know that, I mean, I haven't written the reason, but hopefully you wrote it down in your notebook, that Q disjoint union Q is in bijection with Q, because finite union of countably infinite sets is again countably infinite. Okay, I am going to use this particular argument now, yeah, and I am going to tell you something different and hopefully interesting. So now I want to talk about functions from natural numbers to natural numbers. So if you remember, on the last slide we talked about functions from natural numbers to 2. So using CSB theorem we had this, we showed that using CSB theorem all the points on this, I mean all these sets in this diagram, they are equinumerous with each other, correct, because all of them are inclusions or injective functions. Now what can we say, like functions from n to 2, yeah, that seems to be a smaller set than functions from n to n. Yeah, because we have sequences of natural numbers rather than just sequences of zeros and ones. Okay. So this is, let me phrase this question: is this in bijection with functions from n to 2? So clearly, functions from n to 2 are functions from n to n, because I take a function, I take a function from natural numbers to 2, I can map it to a function from natural numbers to natural numbers by doing exactly the same thing. Maybe I will call it f bar, but f bar just takes n and maps it to f of n. So the image of every such function is just going to lie inside zeros and ones. So this is extension of codomain. Extension of codomain. Yeah, this is extension of codomain. Because the function is a triple. It is domain, then rule and codomain. Huh? No, I am saying the actual value is still f. F bar is the name of the new function because it has different codomain. But what does it do? The rule is still f. Right? The domain is natural numbers, codomain is different. The domain is natural numbers, codomain is different, but the rule is still the same. So it will still map to 0 or 1. Okay. So clearly one side you have, now you have to show the other side, that functions from n to n, well, they have to map inside functions from n to 2 in an injective fashion. Yeah, clearly this is subset. Yeah, by extension of codomain, this is a subset, which means there is an inclusion between them. So now we just need to know the other part. So note that functions from n to n is equal to functions from n to n minus x disjoint union x. Yeah, so this is x where x is the set of functions should I call these functions as sequences? Are you happy with that? It's a function from natural numbers to natural numbers, so it's a sequence of natural numbers indexed by natural numbers. Okay, so it is the set of finite sequences, or maybe I should be more careful, the set of sequences ending in 1 0 0 0 dot dot dot. So basically I am just removing those sequences which end at 1 0 0 0 0. So which means these are just finite sequences, correct? Sequences which end at 1 0 0, so therefore their length is actually finite and the last non-zero entry is 1. So these are basically finite sequences. So x is in bijection with finite sequences, the set of finite sequences of natural numbers and hence it is also in bijection with natural numbers. We have shown this set of finite sequences are in bijection with natural numbers. This is like p-fin argument, yeah, finitary power set argument. Okay, so far so good. So what we are going to show, we will show that this particular set will map into real numbers injectively. Okay, all sequences which do not end in 1000, it will map injectively into real numbers between 0 and 1, and then our argument will be complete. Because see, this function, this maps inside the interval 0, 1. 0, 1 is same as functions from n to 2. Okay, but you will say that, okay, we haven't shown that this full set functions from n to n maps inside that, but the argument is just like this. Even if you remove countable set, it doesn't really matter. You are still in bijection with your original set. And the argument that we will use to prove this red underlined set into real numbers is that of continued fractions. Okay, so every rational number has a unique continued fraction which is finite and which doesn't end in 1, and every irrational number has a unique continued fraction which is infinite. Okay, so that's the way we will prove this. Okay, so now we are going to look at, our question is whether the set of functions from natural numbers to natural numbers, what is it in bijection with? Yeah, we want to show that it is in bijection with the set of real numbers. But for that we are going to use a very interesting technique called continued fractions from number theory. There is an alternate proof which we will see after some time, but first recall that real numbers are in bijection with the set of with any open interval in real numbers, 0, 1 in particular. Then 0, 1 is in bijection with closed 0, 1 as well, open, closed, semi-open, semi-closed. So for this particular purpose I am going to use semi-closed, semi-open interval. It contains 0 but not 1. And then this functions from n to n, what we have seen that we are removing a countable set from that. So we are calling that countable set capital X, and that capital X is the set of all those functions from natural numbers to natural numbers, where for some n, I mean from some point onwards it becomes 1 0 0 0 0. Yeah, it's a function from natural numbers to natural numbers. It's just a sequence of natural numbers indexed by natural numbers, and it is eventually 0, and just before it hits 0 it's 1. So that's our condition. Now we have already seen that this kind of set is in, I mean that it's essentially set of finite sequences of natural numbers. Okay, so we are removing this. So functions from natural numbers to natural numbers is in bijection with this set minus x. We have also seen this proof. So what is this technique? So we are going to start with some real number which could be 0, or it could be anything between 0 and 1, and we are going to associate to it one particular sequence of real numbers called its continued fraction. Okay, we are going to say that the integer part is b, then our next sequence is a0, a1, a2 and dot dot dot. And I will show you how to construct this sequence via this example. So consider the number 13 by 5. Is it a rational number or irrational number? It's a rational number, correct. So 13 by 5 you can write as 2 plus 3 by 5. Now when you write 3 by 5, whenever you get a number less than 1, you have to invert it, and invert it in the denominator. So then you get 2 plus 1 over 5 by 3. Now look at just 5 by 3. It has got some integer part, namely 1, and then some fractional part, namely 2 by 3. So you can write 5 by 3 as 1 plus 2 by 3. Now 2 by 3 is again a number which is smaller than 1. So you invert that. So you will get 1 plus 1 over 3 by 2. Now 3 by 2 again has some integer part, namely 1, and then it is 1 by 2. So now we have obtained, look at the whole expression, 2 plus 1 over 1 plus 1 over 1 plus 1 over 2. Now, I am just going to collect all these integers which are circled. Yeah, we are getting 2 colon, semicolon, 1 comma 1 comma 2, and then eventually it is 0. We ended this process. But we could have also gone one step further and said that this 2, yeah, 1 over 2, this last 2 can be written as 1 plus 1 over 1. So, we obtained another continued fraction expansion for the same number, namely 2 semicolon 1 comma 1 comma 1 comma 1, and this is the expansion, and you continue it with zeros. This is the expansion which contains 1 and then eventually zeros, 1 0 0 0, that kind of expansion. So, there are two different continued fraction expansions for the same rational number. Now, this will always be the case. So, therefore, we discard this one thing and we keep only the one which does not end in 1. It is a finite continued fraction expansion which does not end in 1. We keep that and we discard the other. Okay, that is why the tick mark and cross. Okay, now we do not just do it. I mean, I originally said we take a number from 0 and 1. What will happen in that case? This number b, the integer part of the original one, that will turn out to be 0, so that we are safe to say we are only working with a sequence of natural numbers. Yeah, because the integer part for a given real number, that could be either positive or negative, we do not want to get into that. So, we restricted our attention only to 0 and 1. What will be the continued fraction expansion of 0? It is just the constant 0 sequence, and for 1 we are not asking for it. So, this b will always be 0. Well, let us look at one more example. So, we saw that rational numbers have got two different continued fraction expansions and we are choosing only one of them. Now, let us look at number pi. You know that pi is not rational, it is irrational. Now, what can we do with pi? We take pi is equal to 3 plus pi minus 3. Now, pi minus 3 is a number. What is it approximately, do you remember? 0.14. Okay, so this is less than 1, its absolute value is less than 1. So, we can always invert it. So, then we can write pi equal to 3 plus 1 over pi minus 3. Now, 1 over pi minus 3 is a number bigger than 1 because its multiplicative inverse was smaller than 1. What is its integer part? Well, if you do not have a calculator, then you will not know how to do it, but I am giving you this, this expansion anyway. Okay, thanks, it is 7, correct. So, 3 plus 1 over 7 plus dot dot dot, and actually I mean I have just taken this value from the internet. It is 3 semicolon 7 15 1 292 1 1 1 2 and dot dot dot, and it will continue. Yeah, it will continue indefinitely, and that is a guarantee. So, we are saying that every rational number has a unique finite continued fraction expansion which is not ending in 1, and how do we guarantee that? By Euclidean algorithm. If you look at the expression for 13 by 5, the denominators are always decreasing, yeah, in successive steps. So, therefore, it must end. And on the other hand, for every irrational number, now take it as a fact that every irrational number has a unique continued fraction expansion, and it has to be infinite. Yeah, that is the important part. And simultaneously we saw that x is countably infinite. So, the map that I had written on the previous screen, yeah, the map from 0 1 to functions from n to n minus x, that is actually a surjective map and as well as injective. So, it is a bijection. So, this is how I have proved to you that this set is in bijection with real numbers. Good. So, this is one proof that fun n is in bijection with real numbers. Here is another proof that the same set is in bijection with 1 n. Let me explain it quickly. Yeah, this is much simpler, but I anyway wanted to talk about continued fractions. So given a function from natural numbers to natural numbers, its graph is going to be a subset of subset of n cross n. Yes, all of you know this. But what is power set of n cross n? Well, it is in bijection with functions from n cross n to 2. We have seen this via characteristic functions. Then this is in bijection with functions from n to 2, again by the same exercise, that n cross n is in bijection with n. So therefore we have a bijection here, but functions from n to 2 is in bijection with power set of natural numbers, which we already showed to be same as like equinumerous with real numbers. So this is another simple proof. Understood this? Yeah, I mean, if you want to continue it, like functions from n to 2 obviously embed by extension of codomain into functions from n to n. So this whole cycle, again using CSB theorem, everything there is equinumerous with each other. Any doubts about this? This is perhaps simpler. Yeah, but by this method you don't learn about continued fractions. Okay, so we have finished this topic on equinumerosity. Eventually, when we'll do order theory, we'll come back to cardinalities and how to choose a particular cardinal.